So thank you very much. Francis Wall and myself, John Thompson, are here to talk to you today about climate neutrality, the circular economy, and earth metals. So one of the key things we want to get across is that what we're talking about is predicated on the need for carbon neutrality, obviously to address climate change. And in that context, what we're trying to do is imagine the supply of metals in that context and consistent with the need for carbon neutrality. So we're going to touch on that carbon neutrality concept in relation to energy and the energy transition and metal use. We're going to talk about the circular economy. We're going to talk about the need for responsible, and emphasizing the responsible primary extraction of metals, and finally close with how we can join up and envisage joining up the value chain. So climate change is obviously the result of anthropogenic greenhouse gas emissions, and particularly CO2. And the rise in CO2 over the last 100 years is illustrated on the top right-hand side there. The CO2 is increasing exponentially, as is the energy, and obviously the two are completely related. On the left side of the screen, though, you'll see a slide that shows the rise in metals over a shorter period of time, over about the last 50 years, again showing an exponential rise, particularly of the metals zinc, copper, and steel, or iron ore if you prefer. So there's obviously some relationship there between metal use and energy, and therefore metal use and climate change. Not only that, but now increasingly metals are required to deliver renewable energy and electrification of the mobile fleet cars. And that's going to require significantly more metals. So the exponential increase that we see in metal demand will continue or accelerate potentially in order to meet the goal of carbon neutrality. So if we're going to exponentially increase the amount of metal that we use, one of the immediate concerns is the availability of that metal, how much we have in the ground and how we can exploit it. Now, interestingly, when we look at the graph on the right, you can see the rapid ongoing increase, as we just talked about, of the use of metal. In this case, this is copper data. But if you look at the bottom here, this black line is a steady increase in reserves. So even though we've been exploiting and recovering more and more metal, more and more copper in this case from the ground, we haven't actually depleted the reserves. In fact, they have continued to rise. And the blue line on that graph shows the ratio of the reserves to production, and it's relatively constant. What that tells us is that we've done quite a good job of discovering metals, resources, and converting those resources into reserves, the economic part that we mine, in spite of that rapid increase in production. So at least in the short to mid-term, the availability of the metal is not our principal concern. Our concern really is whether we can provide that metal in a way that's consistent with the goal of carbon neutrality without causing severe impacts. And it's not just about the CO2 and the carbon neutrality, it's all about the full suite of sustainability goals as defined by the United Nations. And they're shown here on this slide. And what we've done here is indicate those goals that can benefit from the use of metals. And obviously the most important one here is climate change, because if we can introduce renewable energy using metals, we will hopefully move away from fossil fuel use and CO2 emissions. However, although many of the metals benefit sustainability goals, there's a number of sustainability goals that can be negatively impacted by the extraction of metals. So we have to address those impacts as well as addressing the benefits. And that's what we're going to talk about today. So we're going to go now to Francis, who's going to talk about the circular economy.
Thank you very much, John, for the introduction. So yes, over to me. And in this section, I'm going to get you to think about with me some concepts of circular economy and how that applies to earth materials. And so first thing then is, I wonder what you thought as soon as we say this keyword, circular economy. I bet if you're a technical person, it probably immediately the thing that comes up into your mind, and if I could have the next slide, please, John, is maybe some kind of virtuous circle and probably recycling, because that's often what we find, especially as geologists and people working on mining and earth materials. As soon as you start talking about circular economy concepts to people, they think recycling. And a big shout out to recycling. It's obviously extremely important. And if we put our minds to it, then we can do it quite well for some things, but it's not everything about the circular economy. There's far more to the circular economy than just recycling. But on the graph there on the screen, you can see that for some traditional metals like lead, for example, we're actually pretty good. About 75% of all the lead that we use, so this is a graph of the input rates to manufacturing from recycling, 75% of the lead we use is recycled material, and that's thanks to the use of lead in car batteries and the recycling of that material. You might be surprised by how low the rate is for copper. And of course, that's because although we're reasonably good at recycling some copper, the amount we're using is going up and up. And so the recycling input rate's not as high as you might think. And look, we're really rubbish at recycling some of these new metals that we need to combat climate change. Things like neodymium for wind turbines and electric cars, and lithium, of course, for energy storage and all the batteries in electric vehicles. 1%. 0%. So there's a lot of work to do there to increase those recycling rates. If I could have the next slide, please. So after that, after recycling, people think that circular economy to do with mining and earth materials must be all about reusing mine tailings and waste. And no, there's much more to the circular economy than that as well, although a big shout out for reusing mine tailings and waste, because we make an enormous amount of it. And I think John will be coming back to that a bit later, but I looked for some figures, and the largest figure I could find, and I found lots of different figures over orders of magnitude. The largest one was 350 billion tonnes per year of waste that we make from producing our raw materials. And that's 20 times what comes out of all the municipal waste from cities. And I found a nice energy site that converted gigatons into elephants. And so I think that's 70 billion tons of elephants. And if their arithmetic about what happens when you put elephants on top of each other is right, then we make enough waste every year to stretch all the way from Earth to Mars. So if you want a different way of going into space, maybe mine waste could be the answer in future. But moving swiftly on, John, please, with the next slide. This is what I might like you to think about is the view of the circular economy. And this is from the Ellen MacArthur Foundation, who are tremendously authoritative on this subject and have lots and lots of materials if you want to find out more generally about the circular economy. And this is their butterfly diagram. Now, if you're thinking, eek, there's an awful lot on that diagram. If you press the next slide, that should obscure for us the left-hand part of the diagram, which is all about biological cycles. And we can concentrate today on the stock management right-hand side of the diagram, which is all about the inorganic materials. And you can see going straight down the slide there is the manufacturing chain, and then the user at the bottom there, and then all the cycles going round to the side. I don't know if you found mining and earth materials on there yet. If you look at the top, that big red truck, which is a very small spot on that diagram and really puts us in our place. Thank you for the spotlight there, John. But to most people looking at that diagram, that's a very small part of the diagram, isn't it? And that's where we are. So we're very important because we're the input to that economy. But that's a big challenge, is to make sure that we're known about on that diagram and not marooned off to one side is miners and people are nothing to do with the rest of the circular economy, because I'd like to convince you in a minute that we're everything to do with the circular economy. And the really important principle that I've learned about circular economy, it's all about keeping high value. So the smaller the circle there, the better. Keeping things in use, selling secondhand, sharing things is the first thing to do, and then gradually down and down the value chain to our recycling, and then finally, into waste or losing things out of the cycle is the worst thing altogether. So that's a diagram. If I could have the next slide, please. I really like this definition of circular economy from the Ellen MacArthur Foundation. And so let's have a look at that then. It says the circular economy is based on the principles of designing out waste and pollution, keeping products and materials in use, and regenerating natural systems. So in the next couple of slides, I'm going to take those phrases individually and have a look at them with respect to earth materials. So we start off with designing out waste and pollution. And here we go on this slide then. So here we are in talking about earth materials. So I suspect a lot of people watching this lecture might be geologists, and we deal with all kinds of characteristics of rocks, and when we're exploring, we determine characteristics like how rich is the ore, its grade, what minerals are there, what's its chemical composition, how big is the ore deposit, how deep under the ground is it, where is it is very important. And all of these geology characteristics are not isolated from sustainable and responsible mining. Many of these geology characteristics are absolutely connected to the eventual environmental performance of any mine in that deposit. And they link together through what we often call geometallurgy, putting the geology together with the processing and mining of the material. And so you see I've highlighted some keywords there, things like resource efficiency, energy use, affects the carbon footprint, water use, what sort of ore is it, how will it be processed, are there environmentally damaging chemicals that might leave the mine site or the ore itself, and this affects actually the health and safety of the workforce and the well-being of the community around. And so getting this right on a mine is really important, and John's going to come back a bit later and explain some of the things that are happening now and that we can do to improve that. And that is real big time, how the circular economy is relevant to people working earth materials. Could have the next slide, please. And so I wanted to pick out one aspect here that I think is very important in circular economy. And so on this slide, I've got a geological exploration drilling rig there, and then I'm showing there the steps that you go through when you're exploring for a new deposit and to open a mine. And geologists and their exploration team would go through a series of a desk study and then very highly regulated series of reports and economic assessments and feasibility studies until eventually you're ready to raise the final capital and open up your mine. And this all has to be done now in a cocoon of environmental and social responsibility, or else hopefully you won't get your money. You certainly won't get the acceptance of the people around. Now, in circular economy, if I could just push the button to get my yellow box coming up here, there's a very important technique called life cycle assessment. And that's really used as a measure, a quantitative measure of all the inputs, say, to a mine site, and then the environmental outputs for that, things like carbon footprint or greenhouse gas emissions, slightly different versions, the energy that it uses, and also things like the dust and so on that can be produced from a mine. All of that can be captured in outputs from a life cycle assessment. But life cycle assessment is used more often, I would say, in manufacturing. It can equally well be applied to mining, and it's a really important way in which we can talk to the manufacturing value chain and ultimately to customers in quantifying the environmental factors of a deposit. And if you press the button, we should go to the next slide to show what research we've been doing recently is we can bring this life cycle assessment technique right back into the planning stages of a mine, and therefore we can predict what's going to happen when you start mining later before anything's been built and that money has been spent. And by doing that, we can try and ensure that the environmental footprint of the mine is as low as possible. So early life cycle assessment to join up with this kind of circular economy thinking is really important. Next slide, please, John. Right, and that's because, of course, at that stage, you haven't spent your money, so that although your data is not as good as when you're actually mining, your ability to effect change is much higher. That's all that slide is showing there. And we think the sweet spot for the technical people out there is around the pre-feasibility study. Next slide, please, John. Now I'm going to pick a second phrase in that Ellen MacArthur definition of circular economy, and that's all about keeping products and materials in use. And so let's pick on an example, and the phone's the obvious one to go for, isn't it? Do you really need that new smartphone that's just come out? It's a very nice reverse snobbery in circular economy that instead of having new products all the time, you hang on to your old phone, your old car, and when someone says, well, that's very old-fashioned, what are you up to? You say, well, I'm a hero of the circular economy, and that's the highest way that you can keep value in a product, is by keeping using it and selling it on and carry on, keep it going. And of course, the mining companies are getting involved in this topic about keeping products and materials in use. Probably more to the end at the moment in the recycling part of circular economy. And here's an example from the big mining company Rio Tinto, who have a new scrap take-back scheme where their customers can send their aluminium back, and they've linked up with a recycling company, and they will put that back into the chain and sell you that aluminium again in what we call closed loop recycling. So earth material providers, miners, are getting involved in the circular economy in that way. Next slide, please. And let's go to our last part, which you might not think applies then to earth materials because they're inorganic materials, but regenerating natural systems. I think there are two important points about that. The first is what we probably thought about as a natural system. I don't know if you're the same, but when I think natural systems, in that phrase, I immediately thought of life, so the biological systems. And miners can be really important in that part, because around mine is a lot of land. Miners are big land use systems, and so they need to look after that and to make sure that you can regenerate the natural systems around the mine site. And here's an example from a company called B2 Gold in Namibia, where they've gone further than that. And while they're mining gold around the mine site, they're actually helping to rewild a lot of the land and really help increase the biodiversity of the area. But of course, our minerals are perfectly natural materials, aren't they? So it isn't just about biological systems. And if I could have the next slide, please. Think about this. There are two views here of sustainable or responsible mining, and they're both good. They're not mutually exclusive at all. And the first one, which is number one with the ring about it, is what we normally think, I think, by sustainable mining. It's, are the mines behaving well with respect to their neighbours? You know, are they keeping the environment clean? Are they helping with economic generation in the area? Are they doing the things that the banks and shareholders need them to do? The ESG agenda? Are they abiding by all the laws and rules? So that's number one in sustainable or responsible mining. But we could just press the button, John, and let's have another view. Is this supply chain or circular economy view? Because our natural earth materials, our metals, they don't go away anywhere, do they? They're the ultimate sustainable materials if we look after them. So all along that manufacturing supply chain, that's really where the circular economy is so important, is in keeping those metals going, because if we look after them well, sometimes it's called material stewardship, they will stay there forever. So although we've taken them out of the ground, they're not going anywhere, they're still with us. And that's the second really important view, I think, of sustainable mining that links in so well with the circular economy. And if I could have the next slide, please, John. So that's to leave you then from this segment with a lovely picture taken by the UNESCO Cornwall and West Devon World Heritage Site. It's a mining landscape World Heritage Site where mining happened in the 1800s, particularly 1900s. It's been going on in this area of Britain for 4,000 years. So think of all the tin and copper that's come out of there, and where is it gone? And in the future, when we're mining our earth materials, where are they going to go and how are we going to look after them? And maybe the miners at the front of the chain can become the heroes, if you like, of material stewardship in making sure that they're right in the middle of the circular economy and looking after the metals so that they stay in perpetuity in use for us. And I think that's the end of my segment. So I'm now going to hand over to John to pick up on one of those themes particularly and talk about the efficient and responsible primary production.
Great. Thanks very much, Francis. Yes, so as Francis illustrated, metals can play a critical role in the circular economy. But if we're going to continue to introduce new metals into that circular economy, we have to do it as efficiently and as cleanly and as responsibly as we can. So I want to talk about that, and particularly three aspects: through the discovery phase, the exploration phase, if you like, the issues around extraction and some of the solutions, and then focus lastly on some of the critical metals. So the discovery problem is finding new resources, and it's not easy. It's very challenging to find new resources. And not only do we want to find new resources, but we want to find those which have high quality. And Francis touched on this in terms of their characteristics that are going to be most suited to dealing with the metals effectively and environmentally in an environmentally sound manner. So quality I've shown on this slide, and what quality really means here is not only the metal content and the grade, which is what we normally talk about, but also the size and the geometry, the suitability for mining, which is the geometallurgy that Francis referred to a few minutes ago, how well the metals are recovered, and is it environmentally benign? Can we actually do a good job of mining without any conflicts with the people, the communities who live around the mine? So those are all big challenges, but they all help to define quality. So when we look for a commodity, for example, copper, this is again a map showing copper concentration in different parts of the world. We obviously focus in on the parts of the globe, parts of the crust that have significant amounts of copper. And so a lot of that are for porphyry copper deposits in Arctic terrains, and then some copper is concentrated very significantly in sedimentary basins, for example, in the copper belt in Central Africa. So we go to those areas, but those are still very large areas. So we still need tools to try and make discoveries within those areas. And we use all sorts of techniques to do that, but they're not all big scale. We even can use microscopic techniques looking at zircon crystals shown in the top right-hand corner of this slide, because zircons actually provide information on the nature of the magmas that produce some of the copper in porphyry copper deposits. So we can use the techniques to analyze those and help us find the most fertile areas for potentially new copper deposits. And we combine that information then with a lot of remote sensed information, big scale geophysical surveys that define the character of the crust down to significant depth, hundreds to thousands of meters. We can use remote sensing to look at mineral chemistry, and we can use geochemistry on the ground to try and get regional assessment of the potential for metals in that area. On the right is a picture of the Bouguer gravity anomaly for the eastern part of North America, and it very nicely defines what's called the mid-continent rift, which formed about 1100 million years ago, which is very significant because it contains large amounts of copper, significant amounts of nickel, and a lot of other metals. So a technique like this zeroes us in on an area that is potentially more fertile, still at a very big scale, but allows us to find areas that we may want to work on in more detail. So once we've selected those areas, we get on the ground and we do detailed groundwork that includes field geology, using our understanding and geological skills of the rocks, combined with geochemistry, geophysics. And we now are very fortunate in the modern world is that we can carry many tools around that give us virtually instant real-time data. For example, we can analyze the rocks with this tool over here, that portable XRF tool, which gives us an immediate analysis of the chemistry of the rocks we're trying to look at. And then we can go through a series of other tools. We can use drones to assess the area at a bigger scale, and then we accumulate vast amounts of data. And once we've got that data, then we have to work on the data in order to find drill targets and try and test those targets as benignly as we possibly can. That generates an enormous amount of data. And this diagram here shows a variety of drill holes over an area of about 1,200 meters across by about 800 meters of north-south on this figure. And within that, you can see all those little squiggly lines. Those are all drill holes. And the color coding on the drill holes is for mineralogy. So the mineralogy has been determined by shortwave infrared spectroscopy, SWIR, and that's allowed the minerals to be determined in this vast array of drill holes. But how do you make sense of that kind of information? That's an incredible amount of information, very useful information, but somehow you have to make sense of it. So you can use machine learning and techniques around machine learning to try and identify the key minerals that are related to mineralization that help you zero in on mineralization. And of course, these minerals also have an impact on how this deposit could be processed when it comes to breaking the rock and trying to recover the metals from it. So this detailed assessment of mineralogy using machine learning is now a key component of understanding the deposits that we work on. We combine that kind of information then with a lot of other information, both at a detailed scale by looking microscopically at the rocks and by assessing the broader picture of the rocks, and accumulate all this information. Sorry, just trying to get my pointer to work here. Accumulate all this information downhole and then eventually into a 3D block model of the deposit that we hope to mine. And that information then tells us how to both design the extractive operation and to operate it as efficiently, as benignly as we can. And the key point here for again, the geoscientists who are listening to this is that this is fundamental geoscience, earth science information, which is being collected at the rock scale, which helps us do a better job of mining these deposits efficiently and effectively. That said, once we get into the mining phase, we have serious challenges. And the biggest challenge we face is just the sheer scale at which we mine in order to provide the metals that society increasingly demands. So these big pits, the big pit that's shown on the left here, are moving hundreds of thousands of tons of rock every day in order to extract a very small amount of copper. So less than 1% of the rock coming out of those holes is copper in this case, or other metals, often less than 1%, which means that 99% or more of the rock is the waste, which and tailings and waste rock, which Francis has also already mentioned. To get from the rock to the waste and to get from the rock to the metal, we have to crush and grind this rock, and that's very energy intensive. It requires driving around big trucks, which use a lot of diesel. It requires using these revolving mills that crush and grind the rock down to the point where we can extract the metal directly from the rock. And in the process, we generate tailings. And of course, tailings are collected now behind tailings dams, and occasionally these fail and give us the disasters, which we can see over here on the right-hand side of this slide here. These are simply unacceptable. We cannot keep doing this. We cannot keep producing this amount of tailings and having these disasters, which can result in loss of life in addition to huge environmental damage. So how do we address these challenges? Well, the good news is there's a lot of ongoing work in the mining industry to look at ways in which we can be more effective and more efficient in how we mine. And that includes electrification, removing the diesel out of the trucks. It includes automation, removing the drivers out of the trucks. And in this picture, the truck on the top there has no driver in it. And all of that increases efficiency and also, of course, improves safety. We can also be more selective. In other words, we can focus on trying to process the rocks that really contain the metals and spending less time working on rocks and using energy to grind up rocks that really don't contain metals. So this picture over here on the right-hand side here shows a big shovel with 90 tons of rock in it being dropped into a truck. And the sensors on that shovel detect the concentration of the metal, such that when this truck is ready to drive away, it can either go straight to the plant to have the rocks crushed and ground and the metal recovered, or it can go to a waste pile or perhaps a pile that may be ore in the future, but currently isn't economic, or it can go to the permanent waste pile where we know we're not going to use it again. And in the process, we end up extracting more metal from less rock and therefore using less energy, and we become more efficient. This is all really part of the conversion of the mines into a modern, if you like, 21st century digital or smart mine that allows us to monitor continuously what we're doing, both in terms of how we mine and process, but also in terms of what the waste is and how effectively we store it. So that is the smart mine that we want to get to. And ultimately, that smart mine will not only produce material at the mine site, it'll take that material all the way through to the metal, so that finally, when the product leaves the mine, it is just the metal, not any other intermediate products. So that's where we want to get to. We want to get to the most efficient and clean mines. But of course, ultimately, it would be even better if we could get away from mining completely, if we could actually recover the metals directly from the ground without mining and without generating any waste. And this is a reality. This is a possibility that's already used for some commodities, particularly for potash and uranium, and is being currently investigated at a number of projects for copper. So the picture over here on your right shows these wells where a fluid is being injected into the ground to dissolve the metals and then being drawn back up to be processed and to recover the metals. Now, obviously, if you're putting in reagents into the ground, you have to be very sure that those reagents can be fully recovered, that there's not going to be any loss of those reagents into aquifers that may surround the extractive site, because obviously it would be a severe environmental problem. But we believe you can get to that point in some cases, and it certainly needs to be assessed whether how efficiently that can be done. But ultimately, this is where we'd like to end up. So that's how we could get to a very efficient, very clean extractive site. But we not only want to extract, the key commodities that we go after, for example, copper in the example that I showed previously. We want to extract all of the metals that are present in that rock. We've put a lot of effort into bringing that rock or bringing a fluid containing the metals out of the ground. So we want to do the best job we can of making sure all the metals that are in that get used. And we're not very good at that to this day. And as being part of the circular economy, obviously we want to be highly efficient in how we do this. So for example, in this periodic table, I'm showing the metals that are typically found in a porphyry copper deposit. And there's a lot of metals, although most of the effort goes to extracting copper and perhaps some byproduct silver and gold in some cases. Some mines, some porphyry coppers also contain molybdenum, and so we not only generate a copper concentrate, but we generate a molybdenum concentrate, and that might, in some cases, have some rhenium in it. But it's not just those key byproducts that we already know about. You can see on here, there's a lot of other products. So in the pale green color, there are byproducts that we don't extract, but could be quite interesting if we could. For example, tellurium or zinc or palladium. It'd be very nice if we could recover those from porphyry copper deposits. And then there are another suite of elements which could be byproducts or could be very damaging to the environment if they got out of us through tailings or through effluent and so on. And these are the ones shown in yellow. So a good example would be arsenic or selenium. These are metals that we need, that we use, but if they get into the environment, they can have very negative consequences. So how do we get to be more efficient in how we extract metals? So traditionally, a lot of those specialty metals are extracted at the smelting and refining stage. And smelters and refiners, to most people, don't sound like very clean pieces of the industrial economy. And certainly in the past, that's the case. So here's a picture of an old smelter refinery about almost 100 years now ago, and it certainly doesn't look very pretty. But that same view is shown over here, and smelters and refineries have made significant progress over the last 20 or 30 years in becoming much cleaner and more efficient, to the point where they are targeting zero emissions and zero effluent, so nothing escaping the site of the smelter. Now, the neat thing about smelters is that they not only recover the major metals here through a process of smelting and through furnaces and electro-refining, but they also recover specialty metals and specialty metal products through some of the waste streams that are related to the smelting and refining process. So some of the metals that I talked about previously, for example, tellurium, can be recovered from these copper smelting and refining processes. Not only that, but because of the nature of these complex smelting and refining, they can also take in scrap material and waste material and bring them into the flow sheet and recover the metals again from them. So the smelters and refineries that have traditionally been the end stage of the mining process now become an integrated part of the circular economy that help us meet the goals that we've been trying to describe. So we go back to what we raised at the beginning with the Sustainable Development Goals. I made the point that we need to address those goals both from the positive sense and to minimize the impact that could be negative. And we need to do that through efficiency and recycling. That's very critical, as Francis described. We need to accept that we will be adding new metal from new resources, and we need to do that responsibly through discovery and then through delivery and recycling. And if we do that, then the mining process, the mining through the smelting and refining process, becomes an important input and a vital input into the circular economy. So with that, we'll just wrap up with a couple of last slides to pull those two pieces together, and I'm going to turn it over to Francis.
Okay, thank you very much, John, for that. So here's the last couple of slides then. It's just to review in terms of the circular economy then where we are and where we can be going. And so I think the first point is that we often talk about mining with one hand and recycling with the other. And I think a point that we would really like to make, and was made very well with that smelting slide that John just showed, is that let's think about raw materials providers, where the new materials provided by mining are integrated and joined up with the materials coming round that circular economy circle. So it's about new and recycled raw materials, so that mining is a valuable and responsible input together with recycling the raw materials providers for a circular economy. And then we have to get really efficient about how we do that, about how we design the materials. We haven't actually even touched on that today, John, so that's another talk sometime, is really joining up mining with the design of materials in a circular economy. But altogether, we have to get very good at joining up and completing that circular economy circle. And I think the other key word that we would like to leave you with today is this materials stewardship word. And I think from the point of view of the front end of earth materials providers, we can very much be part of that and take a lead in sustainable materials stewardship with our brilliantly sustainable metals, our earth materials, which can go on forever if we look after them properly. And then, John, what's our very last message for you as the audience here is one, I think, about collaboration. Because if you see the slides that John showed on the Sustainable Development Goals, you'll see that mining doesn't attach to one particular goal. It faces lots of goals in either a positive or a negative way. And so we thought the last slide would really like to put up SDG number 17, partnerships for the goals, because I think throughout all of the slides here, we've been showing different processes in mining, environmental stewardship, and so on. And this all needs lots of scientists and civil society and governments and investors and manufacturers and consumers, and I've probably still missed some people off there, to come together to make sure that we're really producing our earth materials in a way that's consistent with a circular economy and will really drive all the positive parts of sustainable development for the future. I think that's me, John. I don't know whether you've got anything else to add to that, or whether you think we've come to the end of our session here.
No, I think that's a very nice way to wrap it up, Francis, and just to emphasize again this need for collaboration. These problems that we face in the resource sector in terms of both providing metals and doing it appropriately are very challenging. And the industry has typically in the past been very siloed in the way it's approached that, by discipline, with people narrowly focused on the piece of the puzzle which they are trying to address and trying to do the best job they can. And we suggest here that that's not good enough for the future. The problems are so complicated that we need to work across disciplines with many collaborators and perhaps different providers, different types of companies than we've had traditionally, in order to address the challenges of providing the metals sustainably in an effective, clean manner that then becomes a key part of the circular economy and then stays in the circular economy, with then the mining facilities then helping the return of some of those metals back to new uses. So with that, we'd like to thank you very much and look forward to your questions and the discussion.